All right, tres, dos, uno. Okay, let's boogie. Okay, so here is table of values. Sometimes in a blue moon, you might run into being asked to graph by hand, or being able to just spot kind of relationships between inputs and outputs of any kind, and you're supposed to be able to create a table of values and then just graph it by points and just kind of extrapolate and see what happens to the relationship or sometimes a function. So here we have three examples. We have an exponent example. Notice that the input x is being restricted between -1 and 3. The second one is a log example, so that's logarithms. And there you have the input being restricted between 1 and 5. And by the way, if you want a little bit of an intro to logs, kind of what they're used for, I'll put a link up above, all right? So just in case you want it. Now, the last function, which is the output, is actually MF. You may not know what that is. Maybe it's a mass or final mass or something like that. And it looks like it's actually half-life example of graphing because I see 1/2 there. So in any case, it doesn't really matter in this case because we're just asked for the table of values. So there you have a restriction between 0 and 4. So let's take a look at these examples. Let's create a table of values for all of them, and then let's actually try to graph them in some way. All right, just so that you can get a sense of how they look like. And I will, so just as it says here, use Desmos to kind of check your answers. So we'll use Desmos as well to see how it looks visually in comparison to our graph. All right, so here is kind of example number 1. So I'm going to do a table of values for that. So here is the table of values right here. And I'm going to be kind of picking on this one first. Notice the restriction, which is -1 to 3. So when you're doing a table of values, they actually go, so if on top is the smallest numbers and then they get bigger as they go down. So sometimes people put it in reverse, try to keep the smallest numbers on top and then the bigger numbers as they go through towards the bottom. All right, so you can do that. So here I'm going to say, so here's my input x, so I have -1. I'm going to just pick these, so -1, 0, 1, 2, and then finally 3. So that's where the restrictions comes in. So that's coming right there. Now I can find what my corresponding output is, okay, for those inputs. So it's not a big deal. I mean, you can take out your calculator and we can find what this is. So here is my calculator. So I have 0.5 multiplied by 3 to the exponent of, and in this case, the first table of value is -1. So if I do that, so notice I get 0.166666666, okay, and so on. So I can place that in here, 0.16, I'll put a bar because the 6 is repeating. Now you can keep it actually as a fraction because notice 3 to the -1 is really 1/3. So you have a half. So this is, you know, if you wanted to see, this is 0.5 divided really just by 3. And because you're dividing by 3, sometimes you get the repeater. All right, so that's kind of what it is. And then I can transform this. 0.5 is 1/2. And 1/2 divided by 3 is 1/6. All right, so that's why. So notice here, let me clear it. So 1/6, and you get that value. Now you don't have to do that, but I did it for myself because if I'm going to have to graph it, 1/6 is kind of nice and easy to gauge where it will be between 0 and 1. Now for the next one, which is the input is 0. So in that case, notice we're going to get 0.5 x to the 0. Well, a number to the 0 is 1, right? So this is going to be 0.5 times 1, which is just 0.5. So that's my second table of value entry. My next table of value entry, 0.5. So now my x is 1. So 3 to the 1 is just 3. All right, so now 3 and then times 0.5 is 1.5. So I have that. All right, so this is so far what I have. Again, you can keep these as fractions if you want. So this would have been 1/2. This would have been really just 3/2. That's up to you. Now x, okay, is now 2. So if I put 2 in there, so 3 to the 2 is 9, right? So now 9 times 0.5 is going to be 4.5, or 9/2 as a fraction. And then finally 3 as my input, so 3 to the 3, now it's getting a little bit bigger because it is growing, it's exponential growth. It's going to be 3 to the 3 is 27. And then 27, okay, and 27 times 0.5 is 13.5. And now, if you're not comfortable with that, of course, just use your calculator. So 0.5 times, then 3 to the 3, and then you get your answer. So now because I've kind of stuck here with these fractions, so I can keep it like that. So now with my table of values, all right, if it says graph, okay, so I'm going to graph it. So I'm going to cheat here because I have the tool to change this paper to look like a graph paper, so that's kind of nice. And now, so notice what I'm doing is I want to be able to take these values so I can kind of gauge what I need in terms of my scale for my graph. I'm going to change this up. Now I'm only starting from -1, so I really don't need much, okay, with respect to my x scale. So this is x, and I'm going to draw my y. So notice my y, they're all positive, okay, for this particular example. So this is what I have. So this is my y. So now I have -1, this is 0. And now, okay, so we're going to go 0, 1, 2, and 3. All right, so I'm going to say 1, 0, we already did, 2, and 3. Now I can keep going, but I am being restricted between -1 and 3. So those are the only ones that I will actually graph in here. And now on your scale going up, so we got to go all the way up to 13.5. All right, so notice 13.5 is actually quite a lot. So here this is going to be a little tricky. So let's see if we even have that many. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then that would have been 14. All right, so you can do that. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let me blow this up now here so that you can see it. And now I can go ahead and graph. Now, of course, these are going to be kind of not exactly to scale per se, but, okay, so 1/6, all right, it's basically a 1/6 of 1. So it's going to be very small. So I'm going to remove this. Oh, that's not what I wanted to do. Just to remove that. So 1/6, so it's almost like you have to kind of break this down into 6. So 1, 2, 3, 4, 5, and then that's 6. All right, so my first one is going to be very low, so my point would have been right here. That's 1/6. The next one that I have is a half, and that's at 0. So a half is basically halfway through here, so this is my half right here. At 1, I have 3/2, so this is now slowly starting to grow. At 2, it's 9/2, which is 4.5. So now it's kind of picking up here. And then at 3, it's 13.5. So 13.5 would have been right here. So notice how quickly this skyrockets, right? So basically this function or this relationship kind of starts to go, all right? So it's going to look like this, and now it's really blowing up here. All right, so it's going to go like this, and then it continues on, but we have a restriction. So because of the restriction, all right, so I don't really have this right here. I'm going to stop it right there. So it's from there to there. That is it. Okay, so that's what I have. Now we can check this graph with Desmos, all right, directly. So for example, let me go back here. So I had, okay, so this was, in this case, so it was y. All right, let me put this in here. So y equals Let me switch this up here. It's a little bit easier to type. Okay, so y equals to 0.5 times 3, to the exponent x. All right, so that's what it was. And now we did need a restriction here. So I'm going to put a restriction. So this was between -1. All right. So x was being restricted. And 3. Okay, so notice this is exactly how our function looks like. Now you can kind of scale this how you like it so that you can see it, all right, a lot better. But that's how you would use a table of value and then graph it. So that was our first one that we had there. So now let's take a look at the second one. So how is this one any different? Well, it's not any different. It's exactly the same. So here, let me copy this. I'm going to copy this down here. This is my second relationship, okay, so that I have. And now let me create another table of values. This is between 1 and 5. All right, so let me create this. I'm going to copy it down. All right, so let's say I have that. Now let me erase these values because they're not the same. So my restriction is between 1 and 5. So for this one, so I'm going to go 1, 2, 3, 4, and 5. And now I can go ahead. So what you're doing is you're basically now, so you have, this is log of 1, and then whatever that may be. All right. So this is actually going to be 0. And the reason is because notice that log has a base of 10. Okay, so there's a hidden 10 in there. And then if the answer is 1, well, 10 to the 0 is going to give you 1. But if you are curious, always you can double check. So I can put that in here and notice it's going to give me 0. So this is what we have. And now we're going to do that for all the other values here. All right, so I'm going to do that for the entire values that I have in here. So now next, so I have 2 times log of 2 equals, sorry about that, it's not 2 in here, this is 3. Okay, so we have 3 of that. So let me clear that. So 3 times log of 2 equals, all right, so this gives me 0.903 and so on. Now this didn't tell us what to round to, so you can kind of pick a choice. You can say, let's say maybe 3 significant figures, so we can keep that. So let's say we'll keep 3 of them and then round correctly. All right, so let me do the other ones and then you'll see it kind of in fast forward mode, okay, as I'm doing them. All right, so I'll be right back. All right, so I'm back. Okay, so I just kind of rounded all of them to 3 sig figs just to keep it as I said I would. And now we can go ahead and try to plot this out. Now notice that log, okay, because we had a log, we didn't have an exponent, this isn't blowing up on us. And actually, in fact, what you see is you're gonna have, this kind of curved, okay, image going in. You're not, instead of blowing it up, log actually works kind of the inverse of that. So it's going to start to, slow down as it keeps growing there. So if we were plotting this, so just as we did here, now all of these values, so we're basically dealing between 1 and 5 as our input, and our output, notice, is between 0 and really 2.1. So we can kind of scale it differently. So here, if I'm going to draw this out, so I'm going to draw this out like this. All right, so that's that. And again, so this is that. Now here, so what I'm going to do is 1, 2, 3, 4, and 5. All right, so we have to go there. That's my x, my output y. So here I can scale much bigger because I'm really just, my final answer is 2.1 there. So I can actually do quite a lot here. So here, let's say maybe 1, 2, 3, 4, 5. Okay, so let me call that 1. 1, 2, 3, 4, 5. Let me call that 2. And this way, at least, it's easier for you to graph. This is what scaling is. Scaling is you scale it so it's convenient for you to graph. You don't try to cram things in and then nobody can see anything. All right, so here, if I was doing this, so my first one, which is at 1, so that was 0. So that's easy to graph. So there you go. So that's 0 right there. 2 is 0.903. 2 is 0.903. So it's going to be very close here to the 1. 3 is 1.43. So that's 1.43. So it's going to be somewhere along here. All right. And 4 is 1.81. 1.81. So notice it's going to be somewhere along here. So notice it's slowly starting to peak out. And then 5 is 2.1. So 2, so it's going to be somewhere along there. Now, so this function or this relationship basically starts to look like this. All right. Now, if we continued, you would have noticed that it's kind of starting to, constantly go in that direction. Of course, we're restricted, so we're going to just stop right there. And now, if we graph this, so let's take a look and graph it here using Desmos to help us. So I'm going to clear this one. So it's y is equal to 3 times log of x, and we're restricting this between 1 and 5. So I'm going to do that. Okay, so now notice I'm going to scale this up like that, and that's exactly what we did, right? It looks like just like ours. So it doesn't explode. It's not an explosion like an exponential. Logs actually kind of go and start to peak out. Okay, as you keep getting bigger and bigger. That's a logarithmic scale. Okay, so that's pretty neat. So that was the second example. Now let's take a look at the third example here for the graph. So this is actually another exponential, so that's that one. Except this has 1 over 2. So now 1 over 2, so if you remember, when you're going to be graphing, if it's between 0 and 1, okay, it's going to be a decaying function. If it's above 1, okay, it starts to explode. Now you've noticed for log, okay, it doesn't explode. It actually starts to kind of curl out. So here is my last one that I have, so paste. And you can try these, and start graphing them just so that you visually understand what these things look like. So here is my, let's see if this actually remembers. No, I'm sorry. Here, this table of values, I'm going to copy this down again. Copy. And this time around, I'm not going to talk through the table of values. I think you've kind of noticed, so I'm going to speed it up. All right, so we'll be right back. Okay, I'm going to fill out the table of values so that you can see it. I'm just substituting all the values. Notice my input now is not x, it is actually n. I'll keep it in blue here. And then my output is not y, it is m, so some maybe final mass or something. All right, okay, we'll be back. All right, so and we're back. Okay, so this is the table of values for the restriction given. Notice starts off really big, 45, and then it just is getting halved. All right, so it just basically shrinking. So this looks like it's just half-life problem. And now we can try to go ahead and graph this. So for this one, so if you're gonna try to graph it, again, notice these are all positive and we're between 0 and 4. So I'm gonna, again, kind of pick this off. So in this direction and between 0 and 4. So I mean, 1, 2, 3, that's 1, 1, 2, 3, 2, 3, 4. I mean, I could have even scaled it by 3s there and it would have been, sorry, by 4s and it would have been fine. So this is my X. Actually, this is my N. That's my N because we used N, and then this is my MF. It doesn't matter. It could have been X and Y for graphing. But now here I'm going from 45 all the way down. So this is interesting because I'm going to have to try to scale this off. So let's see. I'm just going to count this. 1, 2, 3. 1, 2, 3. 2, 1, 2, 3. Okay, so I'm gonna try. So let's say by tens here. So that's 20, 30. Okay, so that's 40. All right, so that would have been 50 somewhere along here. Now I don't really need the 50 there. Okay, so I have that. Now I'm gonna push this up a little bit. And now I can go ahead and try to graph these. So at 0, here I was at 45. So 45, so that's going to be halfway between 40 and 50. And then now this just keeps shrinking down. So 22.5 at 1. All right, so it's going to be just above 20 there, somewhere along there. Then 11.25, so it really just starts to shrink down. At 3, 5.62. So kind of just about a little bit above halfway. At 4, I mean, it's getting tiny here. So it's somewhere along there. So notice what happens. This is a decaying relationship. So this just keeps shrinking down. And it would have just shrunk down almost to 0 as we keep going in half and half and half. So again, you know, for this one, it's 45. So if I graph this on Desmos, so let's say I'm going to use y, is equal to, so 45 times, it's a half, all right? So 1 over 2 here. And this 1 over 2 is raised to, let's make sure that this is going to be right. I'm going to put it in brackets, 1 over 2. So close the brackets and then raise it to the x, all right, or the n, all right, n. So that's what we have there. And then we put restrictions between 0 and it was 4. All right, so that's what we have. So I think that this is what we had. So something like that. All right. Now, so notice, so I'm going to really scale this off here just so that you can see it. Okay, so there we go. So that's kind of what we see here, right? So let me just go back. Okay, so this is exactly what it looks like. Now, of course, my scaling is a little bit different than here, but they look pretty much identical. All right. Okay, so thanks for watching. See you in a future video. I hope you found this useful. Cheers, everybody.